go back to your notes for a moment. I just noticed something here. Okay, go to your notes and find this section with the equation of spherical coordinates. This, you find it? Okay. And come here. These two are a mistake. It should not be there. I just noticed it because you don't have a cube, third derivative, okay? Did you find them? This, you didn't write it anyway. Okay, that's good. In this case, double mistake, okay. Yeah, you're not supposed to. Okay, good. Okay. Let me clean this. I'm going to use this equation just to illustrate. Let's take this. Okay. We set this is equal to this. Okay? So we're saying this is equal to C, or take it to the other side, it's equal to minus C. Are we okay? And that we also set to m plus 1. Okay? For which the reasons for which will become clear a little later. Now, when you look at this equation, this is a different way of looking at the same thing. Okay? Solution is a combination of or product of phi and PMN. Okay, and these are the this is together called the Laplace spherical harmonics. Okay, surface harmonics or Laplace spherical harmonics. Okay, let's work on this for just a second here. Harmonics. It's a function of both angles. First kind. Let's write these. Okay. And harmonic functions are expressed as cosine n phi. the difference between them is sine and cosine. Now, again, we have the properties. If you take an integral 0 to 2 pi of phi and 0 to pi of theta, okay, delta ML is, does anybody know what Dirac delta function is? No? Okay. Let's see, now I can, I think, erase this now. Okay, what does that mean? This expression, can you see, or shall I bring it up just for a moment here? Yeah, okay. Okay, just to recap, we're saying using the two different angular functions to represent the theta and phi dependence of the wave equation, and their multiplied or their product gives us what we call the Laplace spherical harmonics. And that can be written in terms of constant coefficients plus two functions, cosine n phi times Pmn, the Legendre function, non-symmetric, sine n phi times Pn. Remember, phi is the solution of A cosine n phi plus B sine n phi. Okay, so these are the solutions. And then we say, let's take a look at these without, for a particular value, okay, without one or two, the same kind. It gives us this integral, okay, the combined integral, phi and theta, delta phi from 0 to 2 pi all the way around, and the other one is from 0 to pi, up and down. That integral will give us 4 pi divided by 2m plus 1 delta ml. Delta is another almost a function, but a representation. It's called Dirac is a famous French mathematician, so we call Dirac's delta function. And if the subscript ml are equal, its value is 1, otherwise it's 0. And what this shows is that in this integral, if the subscripts are the same, it has a finite value. If they're different, it's 0. Another orthogonal relationship. That's all it is. Okay, similarly now, what would happen if we take these with 1 and 2 combination? And let me write, this is just another relationship that one is able to utilize. And I will do some examples shortly. Okay, theta again 0 to pi, phi 0 to 2 pi. And this gives us slightly different result than the previous one. Okay, a lot of different delta functions. And let's see, yes. It might look scary at first, but if you just start substituting the numbers, it comes out very straightforward. And what that says is, if sigma and tau are different, then the result is going to be 0. What does that mean? If this is 1 and this is 2, okay, and what are the differences? You're multiplying sine and cosine, their integral is not going to be a finite value. Okay. There's one more relationship that I'm going to write. After that, we'll take it easy on the angles, and I'll show you a couple of examples. Just a relationship that you may or may not find in ordinary textbooks. So let me just put it, because we probably will go back and use this later, and that is the Legendre function times cosine. Well, we need this. Okay. No, let's go along. Okay. Now, let's look at 3 examples. Okay, when 0, n, and m, and in all these cases they are different than 0. What would happen if n and m are 0? If n and m are 0, what would happen? What does that mean to you? Your throat is not that bad. You can answer. What does it mean if n and m are 0? Okay, guys, think. Where do they come from? What are they involved with? Say again?
No perturbations, maybe because they represent the harmonics.
Now, when you say perturbation, what do you mean? Where do you see N and M? What are they associated with?
I think it's about symmetry.
It's about, okay, tell me more.
When n equal to 0, it's symmetric about
Right.
z-axis.
There is no change, correct, right? Cosine n phi, sine n phi. If n is 0, there's no angular change about the z-axis. If m is 0, same idea. Okay, and what does that mean then? Together, if n and m are 0, if n and m are 0, then it's completely symmetric in terms of angular distribution. That's what it means. That's all it is. But something to keep in mind. Now, so in this case, the zeros, okay, let's toss this. Generated. By the phi coordinates. Lead to n meridians. So if you have a finite number n, it just gives you in the spherical coordinates n meridians. Those are the zeros. Remember, for example, in a plate, you have these sine, cosine function, the zeros. Okay? Do you remember? Sine n, x, etc. Similar idea. In this case, you have n zeros meridians at any particular parallel. Okay? Those are it's a harmonic around the z-axis. Okay. And also the roots of function p, m, n cosine theta to m minus n circles. I should say parallel circles, obviously. So you have here n of these meridians and these m minus n circles. Okay? And those are the zeros. Okay. What you have now is these on the spherical surface between two parallels and two meridians. You have almost like a cubic shaped area, if you will, okay? Sometimes we call these the tesseral. I don't know if you will ever see this, but spherical harmonics. Tessera, I think in Latin means cube. Just reminds you of the shape. Okay? Yeah.
We say that if n is 0, it's axisymmetrical along z-axis.
In this axis,
Yes.
about this axis, yes.
Then shouldn't be m parallels, not meridians.
If it is axis symmetric about this, there shouldn't be what? If n is 0, if you, let's see, where is, yes, okay. If n is 0, it's symmetric all the way around, so no meridians. Okay? You see what I mean? Yeah. Okay. In other words, no zeros, no harmonics. Okay. Any questions on this? This is case 1. The case 2 is when they're equal. Let me see. Yep. Okay, case 2, when m is equal to n. In that case, mathematically we can express, okay, let me just see. Okay. In this case, the zeros coincide with the meridians. The theta coordinate does not generate zeros other than those 4, theta, 0, and pi. And final case is when n is equal to 0, PMN is PM0, and all zeros occur along the parallel circles. And the nodal area turns into a zone of the sphere. A few examples. Let's see if I have. pulsating sphere. This is a very good and common example we'll use, and the directivity is symmetric. When m is equal to 1, we have an oscillating sphere. And the directivity is like that. This is the directivity of pressure as it's moving up and down. Okay? This is, let's say this is the Yet a different example is something like a tuning fork. And if you have the tuning fork, let's see, let me make it in the same direction. Okay, you have main lobes and side lobes. And this is at and you can continue M3. Okay, so these are examples for each shape. Okay, M0, and you can go to higher order harmonics, and they are almost like Fourier series. So using these shapes, you actually build up a complicated angular dependence of radiation from a sphere. In many of the studies, many of the examples, there will be an angular symmetry, meaning N0, okay? This is going to be reasonably common, it doesn't change, but there's an angular shape for theta, and this is what those represent. Okay. Are we going too fast on this? No, yes, maybe, because the next step is the radial solution, the Bessel functions. And after that, we'll start doing some examples. Any questions? Too bad our other friend is not here, because I think these would have been interesting to him. Okay, let's see. Let me erase these. Have we done this? Okay. Now you know everything about this and this. Okay? We can erase those. All right. You know how to handle that. So we'll work on the Bessel functions now. Okay? All right. Let me clean this too. By the way, this might give you a misconception, but usually the higher order they are, the amplitude, relative amplitude will be less as you go into the higher harmonics, okay, compared to the lower ones. And so this is just a relative with respect to itself. What this means is radiation is in this axis, primary lobes, and these are called the side lobes. And theoretically, okay, just for a moment, theoretically, in this direction, there's no radiation with that harmonic at M3, just absolutely zero. As opposed to this one, okay? And you can see here primary lobes and secondary lobes, but there's no radiation at these angles. So these are directivities of sound. And where do you see these? You see these in directional microphones, directional loudspeakers, etc. So you adjust them to get the right directionality that you like. Okay. How many of you have worked with Bessel functions before?
Only for third onward.
Oh, yes. Okay. That's right. You know what trigonometric functions are? You know what exponential functions are, right? Well, they represent solutions of a type of differential equation. And Bessel functions are exactly the same, like Legendre functions. They represent solution of a type of differential equation. They were discovered by Monsieur Bessel, and so they're Bessel functions, okay? And Fourier, same thing. So,
Does it have a tabulated value?
yes. Well, yes. Here's the thing. Bessel functions, trigonometric functions, exponential functions, logs, everything, they always have had tabulated values, okay? And partly because computations were very difficult. Now, hardly anybody uses the tabulations, okay? Because you can easily generate it on your little calculator. So, and a lot of these studies in the past, in the textbooks and so on, were developed, expressions were developed for approximate results, just to give you an idea, because you can't just very quickly enter it into your laptop and come up with what it might look like, what the answers were. Of course, there's a trade-off in this. One, you can very quickly see what it does, but the other one is what I personally prefer. Maybe I grew up with these other style. When you write an equation, and even if it's an approximate equation, it tells you something. So it gives you a general idea about what it means, as we saw on several occasions. You know, every equation, every expression should tell you something. And if you can kind of figure that out, then you're in very, very good shape, because then you have an intuition as a good engineer, a good scientist to develop these. You need to know what looks right, what doesn't look right. If you take an expression and immediately get a solution, well, it's a solution of what you entered. You're not really sure if it makes sense or not. So you have to come to a point where you know something makes sense or not. So sometimes I discover errors later. I look at it, I say, something doesn't make sense. And then you go back and correct it. Okay? Let's see. The Bessel functions are, as I said, solutions of a particular type of wave equation. And if we erase them, okay, if we take the first part of the wave equation after we separated the variables, it was written as, again, it's a second order differential equation. Capital R is the only R dependent part of the variable. We can also write this in a compact form as d square remember C we selected as MM1. This is something isn't right here, but let's see. Just 1 second. Oh, okay. Okay, that's fine. Okay, yep, that's fine. This is a compact form of this. What did I want to say here? Yes, KR is much larger. The reason I also put this together like this, when you look at this quantity here, okay, and there are conditions when this is very, very small. Okay, if it is so small that it can be neglected, okay, and what does that give you? Take a look at this. Okay, if KR is much larger than RR, what happens?
It boundaries to first solution of the wave equation can be represented by harmonics.
Exactly. So for this, then you go back. This is now, remember, an approximation. Okay? For this case, you say, okay, dkr squared. Okay? RR is a function. And what kind of function is that? What is the solution of this? The winner gets something. What would be the solution of this? Something isn't still. What does it look like? Come on. You cannot go home until you answer this correctly. What does it look like? What would happen if you change these variables? Write it differently. Does that make sense? Yeah? What's the solution of that? Come on, speak up.
Isn't it just like the first term in the wave equation? Yes.
Well,
And we do the separation of variables.
what's the solution of this?
A sin y and plus b equals
I'm sorry, say again. A
sin y
sin y, A sin.
and y.
This is
Ah,
what do we saw? sine x, okay,
Plus b equals.
something like that. Or in this case, we haven't put anything here. There's no n. Right? Does that make sense? Have you seen this before? Never. This is the first time? Okay. So, what can we write here as a solution? If you make that substitution, what do you have? Just make a substitution. What's y? Exactly. And if you take it, now this is a particular condition when Kr is very large. And that means at large distances, far field. At the far field, see, without the division by r, it's like a plane wave. But the amplitude changes because it propagates in the spherical coordinates. That's an approximate solution for that. All right, let's go back to the original equation now. No? Okay. Let's go back to the original equation now. This equation, okay, in general terms, it's an equation of the type, let me just write in a general expression that in other calculations you might come across in other classes and such. Okay, this equation is a slightly simpler form of this general equation. This general equation is at the root of Bessel functions. So we apply what's called a Lommel transformation. So instead of y, we write x alpha z sub p gamma x. Okay? when you make a substitution for this, you end up with, let's see, let me just go to the next. Okay, you end up with different representation, and I'll explain what z is in a moment. Now, Cp represents any of the Bessel functions first kind, second kind, Hankel functions, and modified Hankel functions. Okay? So this Z can be any one of the Bessel functions. So the way we equate, okay, by making the following substitutions. We equate the two equations. So 2 alpha is set to -1, beta is set to k, alpha squared minus b squared is minus m1. Then the call it radial solution is the following. This is where the functions come in. E times, let's see now. Okay, this is spherical Bessel function of order m, and this is the spherical Newman function of order m. Time is flying and we're not getting anywhere. Okay. Now, the capital J, capital N are ordinarily the Bessel functions and Newman functions, okay? And they're usually used in the cylindrical coordinates. And in cylindrical coordinates, if you look at it, they are again a function, let's say in this case of radius, and they also decrease with R in a square root fashion. Okay, if you look at the expansions. And the reason I'm getting to that is these are now multiplied by another 1 over R but square root. So you can see the amplitude, whatever it is, the amplitude is decreasing with radius away from the source. So one of the important things in the Bessel and Neumann functions is the radial dependence, obviously. The values change. If you go back and look at your, let's say, math handbooks, or even just calculate, you'll see how they change with different orders. Here, in the cylindrical coordinates, the regular Bessel functions, but with a fraction, okay, multiplied by this square root of pi over 2 times the argument, gives us what we call the spherical Bessel function. Yeah, just a shorthand to express that we use Jm. Coefficient is the same. And the spherical Bessel function and spherical Neumann function. Now, this represents, this one represents standing waves without a source. Okay, standing waves without a source at KR0, at the origin. Whereas the Neumann, spherical Neumann functions represents standing waves with a source at the origin. At KR0. Okay? When you look at the values of these functions, it will make sense. Unless there's a source at the origin, this will not make sense. Okay? And what we do is much like the combination of the exponential functions we have used. By combining these, see this is standing wave. Do you know what standing wave is? A wave goes back and forth. It's just a standing wave. And by combining these, we obtain progressive waves. Okay? Either waves that go out radially or waves that come in radially. And those are called the Hankel functions. Let me quickly, let's see, maybe I can write it here. Okay, so progressive waves are obtained by combining Jm and Bessel functions and Neumann functions. So diverging waves diverging spherical Hankel functions are obtained by just an argument Jm. And we call this Hankel function of the first kind. Okay, Hankel function of the first kind, and that's also equal to the cylindrical, but fractional order cylindrical Hankel functions. What's diverging mean? Going out. Okay, going out. The converging spherical Hankel functions would be the second kind. What will be the difference? Can you tell? Based on your experience.
There will be minus.
Exactly, yeah. Yeah, exactly. Yes. And while we're here, the asymptotic value asymptotic values meaning as z becomes very large, I think that's what it is. Yeah. You can see that an outgoing wave, okay, if z is kr, for example, very similar to almost a plane wave, but amplitude decreasing as the argument has a larger and larger value, like 1 over kr. I think we saw, where did we see it? Yes, when we were looking at the solution of this, when kr is very large, remember what the solution was? 1 over r exponential kr, and that's what this comes to as well. And of course, similarly, in this case, minus, because it's an incoming wave. Okay. Okay, why don't we take a few minutes break and change the tape? Okay.